me a few seconds. Okay. Online. All right. Thank you all for being here. Today, our speaker is going to be Tanmoy Mukherjee. Sorry for my pronunciation. And he's going to talk about concepts as the symbolic interface. And yeah, please, Tanmoy, take it away.
So the thing is that I'm not able to see everyone. That's because of the way I've got the screen allocated. But if anyone has any questions, please feel free to interrupt me so that I can take it slowly. And it's easier for me to kind of also stop and pause and ask questions in general if it makes sense or not. And if I remember correctly, it's 40 minutes of my presentation and 20 minutes of asking questions and answers, right?
Yeah, that's about right.
Okay, cool.
We are flexible, so yeah.
Okay, sounds good. Okay, so what I would like to talk today about is on concept bottleneck models. And the way I personally see it is this particular symbolic interface. But I also will be touching upon two interesting aspects, which is basically, can we actually have uncertainty through these latent variable models? And can this uncertainty be actually embedded through an imprecise probability framework? And that's the kind of the spine of the talk which I'd like to present it. I'm a researcher at University of Ottawa, and I am also funded from CNRS. But please, so there are also other actors who are not named here. And it's my, but there are a lot of people who've been behind the framework, including the PyC team. So I need to be, of course, acknowledging everyone in that manner. I guess I don't need to define, I guess, the problem with large language models. We've got a huge amount of LLMs come every day, but we don't have any legitimate way to understand what's going on inside. The decisions, of course, are spread across billions of parameters in dense distributed representations, and there's no single way to map neurons or weight to human readable reasons. And as we start increasing the models, we also find interesting phenomena. And while it seems interesting, we still don't have any human understandable way to interpret it. So we can only get answers. We don't know why the decision path kind of produces them. We've got, we also, for example, in health, law, and finance, we just have a lot of labels, but we don't know, or we don't know how to interpret in general. So there's a lot of unreliability in general. And of course, there is the aspect of transparency is quite missing unless you inspect the inner workings of these models. So having said that, I think one of the ways where we can look into it is through a design pattern. So Lime, SHAP, and attention maps, and I guess not many, I don't need to explain these terms to everyone here. They're kind of like a fixed black box model. Though I guess Lime was first applied in linear logistic regression models or so. But the explanation is kind of separately kind of taken away from the whole computational path. And it has been shown that Lime in general may not actually reflects the model's actual reasoning. So for example, we noticed that if you take COT and you start trying to explain, perhaps, is there some tokens or the COT actually can be reflecting the model's reasoning, you can see that while the model might be using some of the COT tokens, none of them is actually used for reasoning and vice versa. So if it's to be trusted or not, I think that is one of the problems with post hoc models the way I see it. While if you kind of have a reasoning path embedded into the architecture, which is how like CBMs work usually, there is, of course, a path through which a decision will be made through human readable concepts. That allows also, of course, explanation, especially the human explainability layer comes on very nicely. And there's this also interesting phenomena, which is you can intervene on it. So you can remove a certain concept and you can see that if the decision changes or not. So the reframe is basically the way I see it is there's this neural encoder layer, there's a concept bottleneck layer, which is the predicate form of it, and there's the decision layer. So in a way, I always kind of frame this as a standard triple problems. You've got an encoder which kind of takes perception as a symbol. Then you've got the predicate, the kind of the rule, and then the decision is to say if it's readable or not readable, or a certain yes, no, or in general also regression problems. One of the ways I thought I've recently more started asking these questions is like, there's been a lot of work similar to CBMs. I do believe that CBMs and self-explaining neural networks have been coming around the same time. So one of the ways we thought is, if you take the concept bottleneck models the way as was proposed in CO, you notice that, for example, in my case, the text, there's an input text, and that's what I'm going to be showing in the examples. We've got an encoded representations, which is passed through a bottleneck layer, and then you finally get a prediction. The similar structure is also followed actually by self-explaining neural networks or other similar tools, especially if you look into earlier works which would do topic models or probabilistic latent semantic analysis. The basic framework can actually be written in this particular form, which is basically input, latent layer, and an output or a prediction layer. And then, of course, you can have multiple intermediate layers to say, okay, if it's the bottleneck layer or it's a encoded representation layer, but everything can be rewritten in this particular form, which makes things easy for us to kind of see if all these methods are basically doing the same thing. And that's the reason I kind of like to map it through symbols. So for me, concepts are intermediate symbols. So you have a human name predicate. So for example, service is positive, or the food was great, or the ambience is great, and the label is basically a task label, which is saying that, okay, if it's positive, negative, not known, unknown in general. We've noticed that if you can edit a concept value, you can also see the prediction change. That's pretty much also like if the recent works on CBMs where they changed certain patch and they kind of added a counterfactual, you could actually start seeing a different value altogether. And this allows, of course, for us to kind of also introspect, and see which concepts fired and why a decision was made. This kind of layer-wise separation allows us to kind of go by. This allows the explanation as a layer inside this large language models in general, or other kinds of model. The first part of the work where we wanted to look was, especially in natural language text, was basically to build into interpretable traditions. One is the rational part of it, and one is the concepts part of it. Can I guess, out of curiosity, if just by a simple, not by raising your hand, but tell me if everyone understands the concept of rationals? Hello?
Yes.
Sort of, yeah.
Okay, so let me just repeat it briefly. If you've got a text which says about an input text in general, rationals are basically the token level evidence or the span level evidence. So it's basically which part of the input. So when you look at CBMs in general, concepts kind of gives you a high level attribute. If you can map it back to the input image through patches or so, that's what basically rationals is. It's much easier to, of course, explain this in the natural language processing community. So they've been working on rationals a lot. So it's kind of like going back to the surface form of the training data. So input data attribution in general, and to see that like if the input data is faithful to what is the evidence at a higher level. Concepts, on the other hand, are a higher level semantic attribute. So for example, if you say the food was not great, you could just have like the concept called like taste or flavors, and it needs to be kind of mapping back to the sentence, to the input tokens, the token saying that the food was great or the food was bad, or something of that sort. For us in general, concepts are the one where you can actually support intervention. We haven't done, of course, interventions on rationals because that includes like good data in general. For us, the problem with concepts is not really grounded unless you can go back to the rationals, and that's what we were trying to build. Like, can we ground rationals and concepts at the same level? And that's where we wanted to do. So for us, the spine in general is where and why to look. So that's basically the input layer token evidence. And we specifically looked at uncertainty as a metric. And for us to move from point probability to two different kinds of uncertainties, that is specifically epistemic and aleatoric, is what the question we are interested in asking. So one of for any supervised latent variable model we can kind of represent the intermediate states as an encoder, which is the input part of it. Then you've got the latent part of it, and then there's a task vector, which is going to be saying if it's what's the classification label, or for that matter, regression label for say. So the supervised part is where we give the concept attributes per se. So for every input, you kind of give a latent. In our case, it's the concepts. The task head will consume Z, but not the hidden state in general. So the symbolic layer actually helps you to mediate the decision. That's where the symbolic aspect of it comes into play. And I'll also kind of demonstrate like how this kind of allows us with the uncertainty metric we're talking about, that is imprecise. It allows us to actually look into different types of supervision. And that I'll talk about later. One thing I'd like to highlight at the last slide, if you see, so the instances I can, my mouse, the instances of basically the supervised latent variable model is CBM, which is one instance, SENN, the self-explaining neural networks, and prototype models in general. I believe they're all the same thing. But I mean, I can talk about this later. This is not the main spine of what I would like to talk about. So in the first part of it, which is basically to go from rational to concept to label, I've got a rational selector, which takes my input tokens and selects the rational. I've got a concept mapper, which then kind of takes from the rational to the concept, and then the final classification in general. So selected spans allow us to highlight a particular concept, and those activated concepts inform which spans will be useful to select. And then the concept representation is kind of grounded to the evidence, so you know that which concept was mapped or taken is actually highlighted in the particular input token span in general. So as an example, for example, I would like to highlight like the sentence. You've got like, the room was spotless and the staff so kind, but breakfast costs extra overpriced for what you get. Can everyone see the slide, right? So where the model looks versus why it decides?
Yep.
Okay, cool. So this one is basically the input sentence you see on the pink box, orange box, sorry, and the input tokens which are selected are basically spotless, staff so kind, cost extra, and overpriced. Okay, and the one on the right hand side is basically the semantic attributes, or what we call as concepts. Okay. And these concepts are actually given to us, but not of course, the input tokens in general. Okay. So the challenge for us, of course, was to kind of map from this particular part to seeing that. Oops. Sorry.
I have a question.
Yeah.
So here you said, okay, so there's the tokens that so the data comes annotated with these high-level semantic attributes, basically.
Yes. Yes.
Okay, but you have no idea like what these semantic attributes, what are the downstream tokens that are related to these high-level semantic attributes?
No, we don't have that. No, we don't have that. That's exactly the problem, or the challenge, actually. Sorry.
Okay, so basically you don't have like overpriced, like this is what you want to detect.
No. So as an overprice as a token is provided.
That selected evidence.
No, as a selected evidence, no. We don't. We do not given out in general. And so, this, as you can see, the room was spotless, so it kind of maps to the cleanliness, and you can think of this as a one-to-one mapping. So for every one-to-many mapping. So for every selected rational, you want to map it to a particular aspect or a concept, and that's basically what the green and the orange lines are highlighting in general. One to many, because of course multiple tokens can map to, or multiple rationals can map to multiple rationals can map to one concept, not the other way around. In general, multiple concepts cannot map to multiple rationals. Does that make sense?
Yes, it does.
Others, I'm guessing by no question means also same. So to go back, you are kind of introduce these kind of constraints. So in one of the if you think about the equation we see, we've got like a simple classification law. So these are some of the sites where we kind of inject what I can call as some kind of desired data, so which is basically coherence. You want to make sure that certain amount of tokens are coherent in general. There's minimal. You can of course select the whole answer span, but that doesn't make any sense because that's basically saying that everything is important, which makes no sense. Like then there's nothing to pick up as an important rational or which particular token is mapping to a particular concept, right? There's the faithfulness in general, where you kind of say that you want to have a cyclical nature in general. So every attribute, every concept can be mapped back to the input token in general. And of course, the orthogonality conditions kind of make sure that every concepts and every rationals are unique in nature, and that's the orthogonality embeddings we kind of enforce. Does that make sense?
Yep.
So it was very simple in that manner, and so this is kind of like the high level view of it. So as an example, I mean, I don't have it right now, but we've done some similar examples for VI teams. So for example, we took the recent large VIT B16 models, and we took some patches. And what we were interested to see is that can we generate a similar can we generate a similar token for visual token for a concept. And so, for example, for the CUB dataset, we took a patch of the image. We took the ground truth. So CUB, that's the Celtic bird repository, which is quite commonly used for CBM research. You have the ground truth in general given, so you know where the bird is localized. So, for example, what we noticed that for every concept or for every ground truth, we wanted to find the closest patch embeddings. Okay, or the token embeddings similar to spotless, staff, and kind. And every token was selected completely outside the ground truth. So it would select something from like the tree, everything completely outside the bounding box in general. And it kind of allows us to ask like why. So there is some kind of in text we don't have we cannot talk about spatial orientation, but we do notice that this is not kind of followed in images. Like there is no way you say that, okay, this, for example, if you have something like a wing, can you find which particular part is highlighted as a wing? Turns out that some of the tokens which you get from, at least the visual tokens you get from quite large models which claims very high aspect and accuracy, kind of completely gives away from the image. There's nothing about wings in general which is supposed to not pick it up in general. And to me, that's where the grounding doesn't happen. And for me, I feel like a lot of our things are, I mean, we don't, I feel like grounding is something which we need to care about, but I don't think the current CBM literature, I see a lot of work on grounding. But yeah, that's one of the things I'd like to highlight also. And that's where, so where the model looks, the token spans kind of becomes an important part of it. So going forward, what does this help us in the kind of tasks we look into? It kind of helps us to match mostly black box accuracy. We were like 0.2 points of BERT-based models across data sets. Of course, BERT is not the most competitive we should be looking at, but this was slightly older work. We specifically focused on also like selecting the better rationals. So there are some data sets where you can see that gradient-based selection versus the way we kind of versus standard attention. So for example, when you look into the tokens, you can actually use Bird's attention map to focus, saying that, okay, are these tokens important or not? So we noticed that in terms of the way we framed the problem, we were quite close to the standard attention maps in general. One of the things is also what we noticed was for DBpedia-like topics, especially because it's very easily mapped to concepts, it's much easier to get better numbers there. For problems like sentiment analysis, or for anything with fact checking or so, we noticed that the length of the input data really matters a lot. So this is quite biased against, like, for longer text, the numbers don't come up very high, and the rationals might also sometimes be slightly unfaithful. And that's something we noticed. We are still figuring out why. So one of the problems also we noticed was, if you look at this particular problem, which is like cleanliness and service quality, we notice that sometimes there's a huge co-occurrence of these particular concepts. And ideally, despite giving the orthogonality constraint, that doesn't allow that allows cleanliness and value for money to be, like, if they're specific concepts, to be very orthogonal to each other. But we do notice, like, for example, longer tokens like service quality, the co-occurrence statistic still comes up very high, despite making sure that with the orthogonality constraints. I think we see a lot of concepts kind of activating together, and I think that's something which I find as a kind of like a what's the right word for it? Something like which we need to think about, like there should be some kind of a independent semantic unit or something like that, or an ensemble voting, which we could believe help us to make sure that the co-occurrence doesn't occur that together. So they shouldn't be like all concepts like should be co-occurring together, because that could be one of the leading causes of something which we believe is spurious correlation or spurious noise in general. And that's something which we need to avoid. Right now, we don't know how to do that. And this kind of also helps us that can we actually use some kind of, can we use the notion of uncertainty, so that we don't need to trust only one single number, but we can have a kind of a set-based representation to allow us to understand if it's something which we can use, which could be useful or not. Does that make sense? I'd like to go to the next. If there are questions, I can take it now. Yeah.
It's fine.
Cool. So this also has one of the interesting things is, like, can removing a certain concept break a prediction? This has also been quite a easy thing also to do it in the CBM model. So you remove a concept, does it break the prediction? If you force the concept, does it drive the prediction up or no? So this kind of helps you to look into the interventional aspect of a causal probe for the model. And this also talks about basically, can you turn concepts from the change in prediction in general, which I think is something which I guess Pietro also kind of did in his CBM work. Now I think I'd go to the interesting question of basically, usually an uncertainty score gives you a particular score, but it doesn't allow us to take action on them. And that's what I'm going to be talking about right now. So consider this example of, you've got two different situations. The waiter was efficient, I suppose. This is a very unclear statement. And for example, in a data set, if you pass them through a classifier, it'll say, okay, the review that it was positive is 0.6. But if you look at just the number 0.6, it means nothing. What it could mean are, if you decompose this uncertainty into two separate parts, which is basically an epistemic and aleatoric, you kind of get two different reasons. So one of the reading I can think about is, reading could be that the model has seen very less data, so it needs more examples of any kind of a unsure statement like I suppose or so. and anything more with data would actually help me improve my model. Okay. The reading B is the aleatoric. That is, the text is really not very clear. It's genuinely dexterous in a way, and any form of adding more labeled annotators would actually even across multiple annotators, we would disagree. So we need to kind of abstain away from making such a prediction in general, or basically route to a human who would be much more better equipped to answer this question. So there's been a lot of work where people try to reduce interventions into epistemic and aleatoric. Again, one is the model ignorance, and one is definitely the data that itself is very ambiguous. And if the model, where the model lacks evidence, I mean, we know, for example, there are cases where we should collect more data. So anything to do with model ignorance is basically like by breaking the probability through epistemic and aleatoric, or through the set in general. This allows us to track evidence. It allows us to understand, do we need to track prediction error? Should we kind of track data? Should we make sure that there's ample data? While on the other end, if you look at the aleatoric part of it, one of the interesting aspects is that it should be allowing us to track label ambiguity, and also in general reflect annotated disagreement. So anything to do with human review or so, we should be able to give it to someone who's much better equipped than us, than allowing the model to just base its decision on a number which might be generally ambiguous for that matter. So consider this example where we have probability of a particular action to be taken is 0.7. In this case, for example, we've got an upper and lower probability, and this allows us this width kind of allows us to understand uncertainty slightly better. In the kind of work which we did right now, of course, the best or the most easiest way is to kind of look at the average of it. So the midpoint would be the better answer for that. So you can take the lower probability, you can take the upper probability, and you can just say that the best answer is 0.7, which kind of matches to what we have. But at least the fact that you've got now an unsure in the form of an interval really helps you to make a better decision in general. Okay. So we've got two different set of signals. We've got in the case which we looked at, of course, so going back to the SAMES and the latent space and the classification we spoke about, we've got a frozen encoder which kind of maps through two separate heads. One is basically an ensemble in general, and the other one is a dedicated aleatoric head. In this case, we are given annotated disagreement from a lot of our data. So that allows us to break our uncertainty into the ensemble of H heads and dedicated aleatoric head. Okay, that allows us to get this kind of how much uncertainty is there between annotators. We don't often model that, but that's something very important to model, and we had a specific dedicated head to do that. And in our case, we've got LoRa ranks in general, which can allow us to find disagreement between the different ensembles. And then it's basically you get an interval, which then is propagated through a linear head, and then you get a final classification in general. What is slightly different from prior work is I'd like to go back quickly to one thing, which is this general principle. We pointed this out is that I mean there's been a work of Tanmoy which basically talks about no function can actually recover this epistemic and aleatoric situation in general. So whenever you take P of y given condition on x, you kind of say that, okay, P of y condition on x is equal to an epistemic unit, epistemic uncertainty plus aleatoric uncertainty. But what we think is happening is that if you kind of model in that manner, you kind of go into a geometric trap where you can never recover which one is perfectly epistemic and which one is perfectly aleatoric. And at least what we feel is that if we can just kind of move away from having a conditional probability give you two sums, rather have them completely disentangled. And that allows us to kind of measure epistemic and aleatoric in different ways in general. Okay, so we have different heads just for that reason. So everything is separate. The gradients are separate, and neither uncertainty is a function of px. So basically, we kind of allowed us that this impossibility will not hold for us. Does that make sense?
Yeah.
So so once we have this, when we kind of disentangle or separate the two heads in general, that allows us to get so right now, for example, it's much easier to track aleatoric error with the annotated disagreement on a data set. And we also notice that this allows us to get much better improved baseline compared to, so each signal is able to track its intended target in general. One of the cool things which it allows us is that if you notice on this particular 4 modes we have, it allows us to kind of now take a bit more actionable insight. So for example, if you've got a particular text which says, should I be collecting more data? Should I be pushing it through human review? Should I be automating, or should I be declining? Because we've got now a structural separation between epistemic uncertainty on the y-axis and aleatoric on the x-axis, this allows us to kind of now focus on what do we need to be doing right now. Do we need to be trusting our data based on low epistemic and low aleatoric? Should we be abstaining away from making a prediction? Should we be collecting, or should we be reviewing? So this allows us to kind of have a bit more actionable insight in general. The 4 boxes or the 4 quadrants which we have right now, we don't do it right now, but this can be done. So one can have more like action spaces now, or we at least call them as action spaces. And then of course you can have hate to point it out, but like agent, but like you can have something a bit more a bit more human, a human introduced, where a human could probably have a look at the abstaining at least and reviewing. And trust is something which we believe that can be passed, where you can kind of automate in general. But at least by disentangling this of the from 1 point estimate to now a set, which can now allow us to be disentangling from high to low. This allows us to take a bit more decisive process in general. So one thing, for example, and I'm going back to the same problem, is usually with any kind of a conditional probability, we mostly derive both the uncertainties from the same predictive distribution. And the problem which it allows us is that this kind of correlation happens. So this is a very well-known work. This is a well-known work where this has been demonstrated that there's a high epistemic aleatoric correlation across a benchmark of different post hoc methods, as well as other methods which is also not post hoc. And that's because of this kind of having a conditional probability as a sum of epistemic and aleatoric. And for example, if you look at MC dropout, deep ensembles, any kind of evidential or entropy-based method, they have the same problem in general. So that's what I wanted to point out. You cannot definitely separate or disentangle if you have this one particular function to represent them as a sum. So better way is to kind of actually hold them completely separate. And this allows us to kind of now have disjoint parameters. So phi epsilon and phi aleatoric are completely disjoint. So each head is to be updated by its own loss, and the structural separation also quite works out. So they can all be. I mean, there's decoupling, which makes things much easier in general. So the good thing is that this allows that from high epistemic, so from all the same thing, we notice that the correlation now has kind of reduced. So you've gone from 0.78 to 0.05 right now. There's a huge order of magnitude by just separating these two heads in general. Of course, this is across 5 benchmarks. This should be done. But this has to go across, of course, all the 19. The cross pathway gradients measured are 0, which kind of helps us so that we know that no gradients are kind of flowing across each ones, and that allows us to make sure that nothing is kind of crossing over or or hurting in general. So this kind of holds up this whole disentanglement aspect, which we were very keen to look into. I think one of the things which I'd also like to highlight, and this is a bit more, bit more work in hopefully for the future, and nothing we have answers for this, is I still believe that for any SLVM or what I call a supervised latent variable model, they can be instantiated beyond CBMs. We looked at CBMs in general, but you can also take up your self-explainable neural networks or prototype models, and you can show that they're basically they're all forms of supervised latent variable model, including probabilistic latent semantic analysis and the classic topic model, so based on the evidential aspect. So if all of them can be instantiated in the same manner, we did observe for SENNs also that if you can kind of disentangle their epistemic and aleatoric, the abstraction helps you to make sure that all the same definition and the same architectures and the same results hold. We've done it for CBMs and SENNs. We still need to finish off the prototype work for it. So we don't have proof for the number, like the correlation in general being low. We haven't verified that for the prototype models. I think one of the final things which I'd like to point out was, so we've got this kind of like, we wanted to open up the model or in the form of CBM and SLVM. One aspect to look into it was through the lens of clarity. And the way to quantify uncertainty was through this decomposition of epistemic and Aleatoric-Uncertainty. The last part, or the fourth one, is still under review. So we've got a structural separation or a gradient property of SLVMs. I think this is generally interesting for us because we've started also making sure that with this upper and lower bound of the probabilities in general, we can actually use we can actually do reasoning over predicate in general, and that allows us to help us to make sure there's a bit more symbolic aspect working in play. The supervised concepts are basically predicates. So the way you can read it is through they're more readable, they're intervenable and atomic in nature, which allows us to be generally working with any symbolic solvers for that matter. And I think Pietro and Giuseppe had given an excellent presentation on this. So I think one of the problems which and some of the things which I'd like to make sure that this hopefully would be what we can do in general. I'm very keen to look into the instrument. So the limitations, of course, in some of the work are, it's still concept level supervision. There's been a lot of work into large language model concept bottlenecks or something of that sort, where people say that you need to kind of you can avoid this concept level supervision. The problem is I don't see the problem which I see is like, I don't know then how to measure Aleatoric uncertainty. Right now, Aleatoric uncertainty comes from data sets where we know that there's genuine humans who have differing views or so. We've noticed that with LLMs, I don't know if that's, there is this confounding picture where we know that sometimes LLMs don't really understand, but they actually like greedily search over the text and then they make really absurd decisions. So for me, that's why the first point, I don't see it as a limitation. I'm not sure how to do it actually. So if anyone has a better idea, happy to take that. Rational selection is one of the challenging problems in clarity. It's simple, like, I mean, people use flexible, people used variations of Gumbel softmax to make sure that you can actually do now a bit more easy gradient estimation, or you can, of course, use your straight gradient estimators, but it doesn't really, it's not the easiest because then you'll have to find somewhere, not co-occurring, but like they should be belonging in a certain span or so. There should be, of course, the ambiguity signal to calibrate for AU tracking. That's something which we need to think about in general. I'm very keen towards, of course, like exploring CBMs with rationals as instruments. We are working on that part of it. Interval propagation rules over concepts, that's also something which is very interesting. One of the things which I'm really thinking about for this particular year from 2027 is to think about active abstention, like really ask questions where you cannot answer. And you shouldn't allow anyone like the LLM to answer if it's really like something which is not to be answered. And of course, the last part, larger backbones and how to do unsupervised aleatoric estimation. For me, the last part of having unsupervised aleatoric estimation remains the biggest challenge. But if there are other ways, for example, the most easiest way people would say is to use LLM as judges or LLM as annotators. For me, I find them, they provide more unreliable signals than reliable signals. So that would be one of the challenges I would feel. That's kind of the final part. Happy to take questions.
Very interesting talk. So, I mean, yes.
Yeah, go ahead.
Okay. So can we go back to the slide that had like the prototype models, the CBM and the CNRS?
Yeah.
So,
just
okay. So they differ from one another by the loss, right?
When you say loss, 1 minute. Cancel. Sorry, I just need to go back to the sharing of the thing. Share window. Show all windows. Yeah. Sorry, not this one, but towards the end. No, was it here?
Yeah, this one works. Like anyone that had the three models.
Yeah.
The three
Wait,
classes.
1 minute. Yeah. Go ahead. Yeah.
So they differ from each other by, like, I guess the way the network is structured and the losses themselves.
Okay.
Right. So so I guess I'm not quite sure how you would generalize this to the prototype model.
Okay,
I don't know. Or like, because the main thing is the labels, right? And here the labels are different.
Right. So let me explain it the way I see it. So if you look back to what we had gone back to the first slide, which is basically we pointed out in this manner, which is basically you've got, so if you take this particular aspect that is input text, forget this encoded representation and concepts, and you've got a prediction. Pretty much prototype models, what they do is if you see the K concepts, you have to think about K concepts are the same thing as what they do is in terms of like K-means clustering. Okay. Am I with you?
Yeah.
And then you can use that to make a prediction. So there is a there's a two-layer aspect which kind of allows to map concept bottleneck models with, the way I see it, to prototype models. Okay, the K concepts is a form of dimensionality reduction, which is pretty much what prototype models do. Okay, so in terms of how they read loss function, I believe they're all similar. Okay, that's also at an abstract level. I'll be very, very honest. I'm not saying we've got it all grounded right now, not yet. That's work. I've had conversations with Pietro, and that's something which I'm very keen towards to close the chapter, like as a basic thing. Now going back to SENNs in general, or the self-explainable neural networks. Reading the paper again and again, they've got a multiple stack of what I feel is an encoded representations. The more representations you build on, you're creating multiple subspaces. So one can rewrite the problem if you just go with linear layers. They're basically doing the same thing as like stacking multiple linear layers, and that basically looks like one big giant recursive layer of linear networks in general. So for me, I don't see how, or the way I see it is like they're all quite similar. I don't see any difference between them. I don't know if I'm able to explain what probably from CBMs to prototypes. I don't know if it made clear, but yeah.
Okay.
Does it make sense from the CBMs to the prototype?
It does make sense, but It's just how the loss is constructed. I'm not sure.
But hear me out. Hear me out. The way, if you talk about prototype models, at least the 2017 or 2018 paper, it does it pretty much with the medioid-based aspects. So if you remove this particular H encoded representation, I think from input to K concepts is pretty much the medioid problem in general. There's nothing we're doing different then. If you remove this, sorry?
Yeah, I do agree, but to some extent, like I understand there is a two steps process to go from the input to the output, but I agree with Aya that the semantics of this intermediate layer is different from prototypes and concepts. Like
the way I saw that,
the loss is part of that. Now, depending on the loss, you're trying to impose a specific meaning on what this intermediate layer should represent.
Indeed, but if you look also at the simple CBM models, they have basically, so if you look at the prototype models, again, I'm going back to the 2017 paper, which I remember partially. They had a two-step process of mapping from input space to the centroid, right? And from the centroid back to the input space. That's the loss I remember. If there's something else I'm not remembering, please correct me. Okay? Yeah. So that's pretty much like a K-medioid problem. But the way they capture K concepts is still with K-means clustering.
Yeah.
At least that's what the paper talked about. To 2017 or 2018. I forgot. Was it prototype models or something like that? Or
yeah. I mean, right? Cynthia's paper, I guess. But
also the CBMs do the same thing. So if you are to say that, okay, get me a 20 K means or so, or 20 concepts, which you kind of supervise through certain aspect. So you give that supervisory signal in the traditional CBM paper, then you're basically doing the same thing in general. Like I think the prototype papers, they worked on multiple K or multiple prototype numbers, and that's what they basically did. So I call them under the supervisory signal in general. So I'm not saying, I do know that prototype models, they claim themselves as unsupervised, but that's why I'm labeling all of them as a supervised latent variable model. I'm not saying, by the way, prototypes are the same as CBM. I'm saying supervised prototypes are same as, I believe, are same as CBM. Now I don't know if this makes more sense or still makes no sense.
I wouldn't say it makes no sense. It does make sense, but I guess I'm just trying to see if the argument still holds. That's my only, how I'm thinking.
I personally, so the thing which I think which is good, because now there's a lot more people hopefully interested in this question, or I hope so, is that I think we've got some evidence for it, at least the way we've done from our group. And I'm happy to kind of share this with Pietro, because I did speak with Pietro in the summer school at SI. And I said that this is something which we believe is true, and we're actually using the PyC toolbox for that matter. So I do believe this. We've got some experiments for supervised prototype models. I don't know if there's a name still which exists, which is called supervised prototype models, but I do believe that they're basically doing the same thing. And one can rewrite the loss functions. Though I haven't worked out that particular part, but I guess if anyone's up for probably like in September, once holidays end, happy to share like a proper manuscript with a bit more details and every experiment we've done to make sure this is clear.
That would be great. Thank you.
Cool.
I have a question regarding the architecture of the CREDENCE architecture.
Okay.
So if I understood correctly, there are in order to predict a concept activation, you don't have just one head, you have multiple heads. One
yes.
that predicts the central part of the central point of the distribution, and two heads that predict the variance of the distribution. How do you supervise each of these heads?
you don't supervise, but what you do is you try to inject by simple aspect like dropout. So if you look at this wonderful paper by Yaren Gal, who says dropout is basically some kind of an what's the word for it? I think it kind of helps you to get these variants. So what we did was we started like manipulating the dropout to kind of get a disagreement score, and across multiple heads in general. Okay, so think of it like you've got one head, you put a dropout mask of, let's say, 0.5, change it in kind of think about like adding another weight vector by some random noise. So you can think of like injecting your weight space so that it starts growing and seeing like how your prediction in general, or the variance in general for that matter, is changing. And that's what's important to capture in terms of model disagreement. Does that make sense?
Yeah, but how? So if I understand correctly, you have a dropout both on the aleatoric and the epistemic head.
Only on the epistemic.
Only on the
part of
epistemic.
it.
Okay.
The epistemic, yeah.
Okay,
and that's to initially.
Okay.
In the aleatoric, it's a simple head because it's basically we have annotated disagreement right now. So in the data sets we looked into, we had the annotated disagreement. So this is something which I think, if you remember, we spoke about this wonderful data set in NLP, which kind of does it's basically used for causality studies, and the reason is because it's got annotators aligned with it, and this is called CBAB as a data set. Which I think we spoke very briefly at the summer school. So so in that case, we haven't done that. Like we haven't put so we haven't tried with multiple aleatoric head or something. It was because we've got a head which measures Aleatoric-Uncertainty or aleatoric or annotated disagreement. I think it was easier for us to kind of look into that aspect, like to get that metric very easily. While for ensembles, it's just basically a simple multiple heads with multiple dropout values to see how much disagreement. Just to give another interesting inspection, which I haven't pointed in the slides, but if you look in the paper, you'll notice that ensembles have a very funny or peculiar property. You start increasing the number of heads, you might see an interest or increase in accuracy or performance, but after a certain point, the number drops out. So there was a saying that there's some kind of overfitting probably happening in general, in the community in general, people who work on ensembles. So this is, I think there's a huge community for ensembles in general. Contrarily, what we found out is that if you do some kind of a geometric, like if you think of the simplex of agreement, disagreement, or agreement, disagreement, or non-disagreement, or like 3 simplex classes, you can see that actually you can improve much better. You can go to an infinite limit and you can explain why this failure is happening. But that we haven't yet written it concretely. We showed with evidence that increasing heads, we see a failure or drop in accuracy. Why that's happening, we haven't explained in the paper, but we think that that can be explained through this geometric perturbation, which we call. So we kind of intentionally perturb our dropout rate, and kind of think of it as a line search, and then you start saying, okay, I'm going to drop by a certain factor, and then you can see that the dropouts over infinity will explain why you need how you need to make sure that the numbers could be better or not. Yeah. I think Giovanni has a question.
Yes, can you hear me?
Yeah.
So I have, I think, a few actually. So I would.
Okay.
If we have time, do we? Actually, we have very little time. But yeah,
I think you like as long like.
I have time.
I think we can go even longer than the hour. So.
I mean, I will try to be quick anyway. But yeah, thank you. So first, I had one on the first part of the talk about like the input attribution kind of part, right? When you were trying to relate rationals, I guess you term them, and the concepts. And I was like, what if a concept relate to something that is not localized in the or in the tokens or in the image, but like it's spread across the, it's like if my concept would be blurriness, for example, and it's not really localized, it's something that you have in the whole image, or it would be something like, I don't know, something describing the tone of the text, and that you would spread across it. So it's like if you had any insight
on it. Yeah, of course. We tried working with the disentanglement literature because we do know that that's very commonly observed there. So you take an MNIST image, you can find factors like rotation, angular rotation, blur, colored objects or not. We tried doing that, but the problem is that I don't think I have a clear answer, because sometimes what happens is if you look at things like beta VAE or all those VAE-like literature who work on disentanglement, and they have these specific aspects which are not in the text. So it would be like shape, color, and things like that. I wanted to kind of bridge the community at one point. That was last year. But I noticed like I was not getting anywhere, and everyone has their own separate metrics, and I felt that it was so. Ideally, if your question is, do I have an answer for like how to kind of get concepts which are not there in the text but might be there in terms of like say tonality and things? No, I don't have an answer for that, and I don't know also how to include that for that matter. One thought process which could be, I don't know, useful is if you can take the continuous counterpart of CBMs. So in place of framing it as as a sum, you can have an integral problem. So you can think of like just using a latent variable model, and you have infinite concepts, and then which concepts are there in the space or not. That is something we have tried, but we're not able to make any headway with it. Like so if I understand correctly the question, like for concepts which might not be in the text per se, for example, tonality or I can't think of anything right now, but like
but they can be like, they are kind of in the text, but they are not localized. Like you cannot really patch you cannot really link to a specific word or to a specific
like style of writing, like if it's Calibri or Arial or something like that. Yeah, exactly.
Maybe you have some conjunctions telling you that, but in general, like in images is with blurriness.
In images in problem is that also, like if I had, like for example, you take your classical CUB dataset, at no way with and we've tried this. Let me share my GitHub link so that I show you guys like with some random stuff we've been playing around with. If people have time, if you don't, please, you don't have to look at this. But we were looking at we were doing some stuff for. Let me just show you the CUB like data set. Let me share my screen again. Allow to share window. Voila. So can you guys see my screen? Sorry. Can you guys see my screen?
Yes, I see it blurry. Wait.
It's a bit blurry, but I think it's gonna settle down.
Hold on.
It is slightly improving.
Okay. Let me just check it once more. Is it much better?
Yeah, it is.
Okay.
At least I
so
can see
look
it
at this one. Okay. So look at this one, which is basically like so what I did in this case was, you've got an American, I don't know if you can see the name of the class of the bird, American pipit, blah, blah, blah. And you can see of course, we took the high resolution part of the image, but everything behind it is completely blurred, right? In a way, you had the ground truth for this particular BIT. And we asked the simple question that from the class classifier layer, pick up the best cosine, pick up the top patches, 16 by 16 patches, and tell me all that are useful for me for that matter. And look at what it started picking up. Okay, and this is the GradCam visualization, the heat map scores which we are seeing out here. And almost all the tokens are completely outside the box. or the ground truth. The ground truth is, of course, I didn't mark the ground truth, which is again my fault. But while we are doing some kind of work where we want to localize this kind of faithfulness. Now, as you pointed out, I only have like 312 attributes given to me. I cannot discover, saying if I pick up certain part of maybe the bottom part of it, to say that, oh, this is kind of like blurry, or this is kind of defocused, or something like that. Like cameraman was bad. Probably I could have said that, but you see, like it's not easy to pick it up in general. And we kind of also put a constraint, if you remember, that every rational can map, multiple rationals can map to one concept, but vice versa will not work out. So sometimes you can have no rationals mapping to certain concepts, and you kind of throw them out, because then the search becomes very complicated. Otherwise, you'll have infinite search in general, or large search space, and you want to kind of reduce that.
Is it something you impose to make things easier, or because it is
you can. So there, I think you can, but having said that, this becomes a very domain specific problem then. So you cannot have like a generalized rule for this. Then it becomes like very domain specific problems, like can you use some kind of a concept hierarchy or something of that sort to kind of pick up the most important, or kind of remove all the useless components. But let me ask you a question the other way around. Let's say that I've got this particular image right now, the one on the left hand side. If I were to ask even among the audience here that, okay, what are the, like, give you certain X amount of concepts, pick up the top 10 concepts, we'll see that there's many of that will not match, especially given 312 attributes. And let's say I've added 20 more, because by saying blurry, cameraman was not very focused, or whatever it is. So all these things then start becoming a bit more complicated as a problem. In fact, interesting, but also like, I don't know how to kind of add that in general. Surprisingly, as you pointed out, in the disentanglement literature, so more like beta VAE and all, they have a lot more better metrics for this. But they don't pick up concepts. They want to find, like, they talk more about generalization. So something like, blurry, green color, and things like that. Here you more focus on the bird and the what looks like wood or something like that. You focus more on the bird. You don't focus more on the background and things like that. Does that make sense?
I see. Yes.
So yeah, so I have no clue. So I gave you a lot of like things, pointers, by giving you no answer. But yeah, I have no clue how to solve this problem, to be honest. So that could be one answer.
I was just curious. There are a lot of there are a few works in CBM that are also trying to like ground the concepts in the input, and yeah, I think they all assume kind of locality in some sense input, which
what we found out is that it's if you do this now for medical images, so we of course are playing around with medical images also, we noticed that, for example, with lesions or so, it becomes much more a complicated story. In fact, completely, like, even with medical trained images, you completely can focus on a different thing, which begs us to ask questions. Okay, can there be some other, can we rethink about this whole gradient attribution map in general, or heat map in general? We need to rethink this problem completely. I mean, we just get great accuracies. We don't know what to do with this thing. There's nothing to intervene on if my concepts cannot. I mean, I do not pick up lesions. I do not pick up specific points of this diagnosis or prognosis, which is to be intervened on. I don't know then what to do. This question, once it moves to, so with birds, hopefully, like, you can change something in the bird, you'll get a new fancy bird. But if you were to do this with real pathology images or with cell types, it's a very noisy story. And in fact, that's where things like blurriness and stuff, so you can actually go and remind yourself that my image is blurry. I need to rethink this problem slightly different, or get me a better image. If you were to decompose this concept into a bit more intervenable manner, I think that really helps us. We haven't done that yet, so I cannot claim that I've got numbers for that. So I've done it for stupid things like sentiment analysis or so. I call it stupid because, restaurant bad or bad should hopefully be no problem. But we need to rethink this problem slightly. And I think that's something which I hope Giovanni or others from from the group in general can pick it up and say that, okay, we've got some answers for this, partial answers for this.
Yeah, thank you. I will go to the next question, which is on the annotation disagreement. And I didn't pick up who is responsible for giving you multiple annotations.
There's a data set, and it's called CBAB. Perhaps what I'll also do is highlight the data set because it's such a cool data set.
Yeah, I know CBAB. It's the one about the ratings, right?
Exactly. And the good thing about it is, like, you will see if you let me share my screen again so that people see this again. Allow to share window. Share this window. So if people can see my screen, this is how the data format looks like. So you've got review majority. So there's 1, 2, 3, 4, 5. And then each one of them is mapped to, if it's a negative, positive, unknown, oops. Sorry, this is to the review majority in general. So that's noise, the edit types in general. And then for each food aspect, you've got negative, positive, unknown, no majority. So you've got all this kind of provided to you.
Yeah.
Okay.
And in the general case, how would you?
Same. Oh, in general case, that's the question which I think I pointed as a future question. I don't know.
Yeah, you mentioned the LLMs, and I was just curious about if you use different LLMs to annotate.
So no, not only that, we noticed that they're not reliable. So not only that, they're not reliable. So what we noticed was that they start picking up they don't understand the text, but they just read the text. And if you change the text by paraphrasing the fake text and making it shorter, the LLM's annotation review completely changes. So as an example, you could say that, let me think of a very weird example. So if you take a sentence, let's say the food was, what can I say? Like, okay, the food was great, but the food was great and the wine was great, blah, blah, blah. If you just kind of paraphrase it to say something like the food was fabulous, the LLM as a judge, if you were to use Mistral or someone, they'll be biased against it based on the length in general. Right now, the problem, what I was trying to highlight as the last point, is I don't know what to do in these cases or I don't know how to handle this, because while LLM as a judge seems very attractive as an answer, if they're biased, then you also know that your annotated disagreement will be completely biased for that matter. And then you'll need to think about some kind of an unbiased measure to make sure that that doesn't creep in for the sentence. So it opens up a Pandora's box the way I see it. I'm not sure how to handle it, so I haven't touched that part. I'm working with some students who are helping us to focus on that particular part. Like, okay, can we see that the LLM as judges can have like some biasness creeping in? Can we do some kind of a debiasing stage or something? Right now, I have no clear answer. I think that I'm always looking for annotated data sets. That's just to kind of give me this signal better. But I do believe that there are some recent works I saw on Archive which talks about this, like to kind of debias LLMs in general. That could be interesting. Again, with different modality, I don't know how they'll each behave. Like between a 3B, a 7B model versus 70B model, they have different characteristics. What they pick up, that's also another problem. Like, you don't want to touch on something and then suddenly realize you've created more problems. So that's one answer. Like, again, I don't have an answer, to be honest. Yeah.
It's just so there is an implicit assumption in the architecture you propose that the annotators are equally good. So
I don't say that. I think they give the reviews. No, they give the reviews. So you kind of also say that, for example, I made my problem more challenging. If you look into the dataset, they have this particular part which is called no majority. So there is no one who's agreeing on certain things. I actually took that as a signal. So I could just say that, okay, cut out all the reviewers who are not sure. I don't want anyone who's intermediate. But then the question is like, okay, what can we do with this? Now, one aspect which we have a group in Lille who work on Markov decision process. So we were discussing with ways where they work on for botanists to kind of look at different plant species. And we were discussing ways, if we were to decompose our uncertainty into 4 different metrics, can we train our models? So for that matter, can we train our LLM as annotators to be a bit better unbiased? Or can one good model train others in a supervisory manner to make sure that they're all doing unbiased? So they're actually reading the text and not picking up surface form or something like that. That could be one aspect we're discussing, but we have we have still no clue for that. We're still working with a postdoc of his, but we have no answer for that. But that is one idea potentially we could utilize. But yeah.
I see. Thank you very much, Tanmoy. Thank you. I will.
Okay. If there are no other questions, I think we can thank Tanmoy for your time. Thank you for your presentation.
Thank you, everyone. Thank you, everyone. Thank you. Ciao.
Ciao, then. Bye.
Thank you.